In this example, we're asked to find the Taylor series for cosine of x about x equals 0. So we're going to approach this in the same way that we did for Taylor polynomials. So we have f at 0, right? F of 0 is cosine of 0, which is 1. All right. So, and then we can find the derivatives. And the cosine has a nice pattern of derivatives. The first derivative is going to be the negative sine of x, right? And then the second derivative is the derivative of the negative sine, which gives you the negative cosine of x. The third derivative is the derivative of negative cosine, so now that's equal to sine of x. And the fourth derivative, I'm going to write it as like that, is equal to cosine of x. Okay? And then if we went the fifth derivative, now we're back to cosine and we're just going to start over, right? So we're going to come back to this negative sign and then we have this nice cycle of derivatives. Okay? So I'm only going to go up to the fourth derivative. If I need anything bigger than the fourth derivative, then I know that this is going to be the fifth derivative also, right? So this is the fifth derivative, and this is equal to the sixth derivative, and this is equal to the seventh derivative, and this is equal to the eighth derivative, right? So I can just continue the pattern if I need higher derivatives. All right, so let's find the values of these derivatives at 0. So sine of 0 is 0, so that's just 0. The second derivative at 0 is the cosine of 0, but it's a negative cosine of 0, so it's a negative 1. The third derivative at, at 0 is, again, it's sine, so it's just back to 0. And then the fourth derivative of 0 is equal to 1. All right, and it cycles again. So let's write our Taylor polynomial. We can write our Taylor series. We're going to write the Taylor series. So we got f of 0, which is 1. And then we have f prime of, if we just plug it into the formula, f prime of 0 is 0. So we don't have that second term. We don't have a first order term. And so now we have to go to the second order term. So the derivative is negative 1, and then that's going to be divided by 2 factorial, and then x squared. All right. We go to the third order term, the third degree term, and again, the third derivative is 0, right? So that third order term goes away. And now we can go to the fourth order term. The derivative is 1, so this time it's positive 1, and now it's going to be over 4 factorial. All right? And we can just keep going, right? But now notice we only get the even, oops, I forgot the x to the fourth. So we can keep adding more and more terms because we kind of see a pattern happening. We're not going to have any odd degree terms. They're all going to be even. So the next term is going to be negative because it's going to be the sixth derivative is negative 1. And then it's going to be the negative 1 over 6 factorial times x to the 6th. And we're not going to have a seventh order term. Then we're going to have an eighth order term. So that's going to be a positive 1 over 8 factorial x to the 8th. And so on. I probably added more terms than I need, but it's nice to see the pattern. We have these alternating signs, and the factorials are all even, right? We could actually think of this as 0 factorial, and so you can see the even pattern. Also, the powers are all even. So there's a nice pattern going on, and it'd be nice to be able to express the kth term, and express a general term for this series. All right, so, well, I definitely see even numbers in the denominator. So if let's just say I let k equal 0, 1, 2. Oftentimes it's just easier to start with 0. So I'm just going to start with 0 because I can see, well, it looks that 1 could be 1 over 0 factorial. So now if I want even numbers always have a factor of 2 in them, right? So they can always be divided in half. So if I take any number and multiply it times 2, I get an even number. Okay, so the first even number, well, if you start with 0, the 0th even number is 0, and the first even number would be 2, and the next would be 4, right? So 2k will give me even numbers. So that has a factorial on it, right? I want an even number factorial. Make sure you put the parentheses around because you want the whole quantity 2k factorial. You don't want just k factorial. You want 2k factorial, and so make sure you put parentheses around it. And then we have this x. We also have this x term, and then we have it's to an even power. So again, we can just use 2k. All right, and then we'll get the even sequence that we want. Then we have to take care of that alternating sign issue. All right. Now, if I raise -1 to a power, right? The key there is just use -1 and raise it to a power, right? If -1 is taken to an odd power, it's -1. If -1 is taken to an even power, it's +1, and that'll give you the alternating signs. So what I'm going to do is just take -1 and raise it to the kth power. Okay, so there is a general term. Now, you might have to do some playing around to kind of get your general terms to work if you are asked to write a general term. Some are easy and some are not quite so easy, but it's always, you can go back and check. Put in k equal 1, 2, 3, 4, and decide if it's giving you what you want, right? So if I put in k equals 0, I get -1 to the 0, which is 1. I get 0 factorial, which is 1, and then I have x to the 0, which is 1. So that makes the 0th term 1. If I put in 1, right, I get -1 to the first power, which is -1, over 2 times 1 factorial, which is 2 factorial, and then I get x to the 2 times 1, which is 2. So you can see that if I put in those k values, I get the values that I want, right, that match the values in the Taylor series that I've written out up above here. All right, so the next one is for you to definitely try on your own, but I'll record a video if you want to see it worked out.